we've got the disk method. And the formula for the disk method is pi times the integral from 0, or from a to b, of f of x squared dx. And a good way to remember that is with the formula for the area of a circle, which is just pi r squared. We have our pi, we have our r, and we have our squared. So basically what we're doing is, so we're finding the volume, but essentially what this formula means is we're taking the area of a bunch of circles stacked together. So like if you had, like, imagine a circular piece of paper, and if you stacked a bunch of them, eventually you're going to get like a cylinder-like shape just by stacking a bunch of papers together. So then you have a volume. So essentially what we're doing is we're taking the area of a bunch of circles and adding them together to get our third dimension to give us the volume of the shape. So in the case of our problem, we had f of x equals 4. We'll just move on to the next page. So we're integrating from 0 to 4 of f of x, which is just 4, dx. Oh, and don't forget to square it because we're squaring our radius. So we have pi times the integral from 0 to 4 of 16 dx. And the integral of 16 is just 16x. And we got to plug in our bounds, so we get pi times 64 minus 0, because 0 times 16 is 0. And then 64 times pi is 64 pi. So we get the same answer as what we did when we did geometry. Now we won't always be able to find our solution using geometry. We'll almost always have to use calculus, but it's cool to see it work like that when you can do it. It's a nice shortcut sometimes. But we'll do one more basic shape, and we'll move on to some more complicated ones. So we have our graph, and we're going to do f of x this time, or f of x equals x this time. So f of x equals x looks like that, and we're going to do it from 0 to 3. So we'll say 3 looks like that, and that is our shaded region, and we're revolving it about the the x-axis. There will be times where we're going to revolve it around the y-axis, but I'll get into that later, because that's where you have to think about it more. All right, so revolving it about the x-axis from 0 to 3. So doing it the calculus way, we've got 0 to 3. Don't forget the pi, that's important. X squared dx, right? Because our f of x is equal to x. So let's see, we've got pi times the integral of x squared dx. The integral of x squared, let's see, is x cubed thirds, right? Because that's chain rule reverse, and those are our bounds. So that equals pi times 3 cubed, which is 27 over 3, minus 0 over 3, which is just 0. 27 thirds equals 9 times pi, and we get our answer. Now in this case, you can also use geometry if you think about it as a cone. So let me draw this again. X-axis, y-axis, z-axis. So we have f of x equals x. And if we're going to rotate this shape, it's going to get to here. It's going to get to there. It's going to get to there. And it's going to generate what looks like a cone. Just draw it off to the side. And our height is going to be this distance here from 0 to 3. So h equals 3. And our radius, r, is going to be the height of where it ends up. So it goes from 0 to 3. So f of 3 equals 3 because f of x just equals x. So our r equals 3. The formula for the volume of a cone, let's see if I remember this. I think it's just pi r squared h over 3, I believe. So we have, let's see, pi r squared times h, which is also 3, over 3, pi 27 over 3. So we get 9 pi, again, just by using geometry. We get the same answer. So it's cool to see that you don't always have to use calculus. Most of the time you will, as we will right now. So moving on, we're going to get a little more complicated. We have f of x equals x squared. So we do the same process every single time, just use the formula. So, oh, I gotta say our bounds. Let's say from 1 to 3 this time. Change up the bounds a little bit. So we got 1 to 3. And also problems will tell you all of its bounds, so it would also say that it's bounded by the x-axis. I'm kind of doing this shorthand, but I'll give you some more real examples once we've gone over the basics. So f of x equals x squared, so we can just do our formula again. So pi times the integral from 1 to 3 of f of x, which is x squared, and we're squaring that, dx. All right, so we got pi times the integral from 1 to 3 of x to the 4th dx. The integral of x to the 4th, doing chain rule in reverse, is x to the 5th over 5 from 1 to 3. And 3 to the 5th, oh boy, I don't know that in my head. So pi times 243 over 5 minus 1 to the 5th, which is just 1. So then we get 242 fifths pi. So a little bit of an ugly answer, but pretty simple other than 3 to the 5th. That was probably the hardest part of this problem. Had to get my calculator out for that one. But yeah, so same process for everything. And you can just do every single problem, every single basic problem this way. So I'll do one more, and then we'll get a little more complicated. So we've got, let's see, f of x equals root x. And we're going to do it from, we'll go back to 0 and to 4. And it's bounded by the x-axis, and we're revolving it about the x-axis. So let's do our formula once again. Pi times the integral from 0 to 4 of f of x, which is root x squared dx. So this one looks pretty nice because our root cancels out. So we just get x dx, and that, the integral of that is x squared halves from 0 to 4. Plug in our bounds, we get pi times 16 over 2 minus 0 over 2. So we get 8 pi for that one. Pretty quick one. You should always try to simplify this out, because often it will make it much easier, especially if there's a root in there. But okay, we're going to switch things up, and I'm going to give you a more complicated problem. It's not going to look as complicated, or maybe it will. Let's get some straight lines up in here. So we'll have f of x equals, we'll do 4 again. And this is going to be bounded by the following functions. Y equals 1. Y equals, y equals 1, x equals 0, so the y-axis, and x equals 4. So let's draw this out. We have f of x equals 4, which is just a straight line. Nice and simple. Bounded by y equals 1. Okay, so that's a line right there. We've got x equals 0, which is just the y-axis, and x equals 4, so right about there. So it's this shape. And we're revolving it about the x-axis. Okay, so you might be able to see the problem here. If we're going to revolve it about the x-axis, we're left with this gap here. So this would actually generate a cylinder with a hole in it. So it looks like a toilet paper roll. So if we're looking at it the rotated around, this distance here would be our f of x, and that distance here would be our hole. So this distance is the same as that distance, and that is the same as that distance. A lot of arrows might be a little confusing, but hopefully the math won't be confusing. So we could actually use geometry again in this situation. We have f of x equals 4. So this distance equals 4. And we have a height of 4, a length of 4, I should say. So then we could just do pi r squared h, which we found before was 64 pi. And we would have to subtract the whole, which has radius 1 and height 4, or length 4, which pi 1 squared times 4 is just 4 pi. 64 pi minus our whole, which is 4 pi, equals 60 pi. So pretty cool that you can do that with just geometry as well. But, of course, it's going to get more complicated, and you're going to have to use calculus. So here we have to take into account the whole that is generated, and we have to use a new formula called Washer method. And you should write this down. Integral from a to b. Don't forget the pi. I've been doing that often. Of f. Oh, sorry. Went back to disk method. Of r squared minus little r squared dx. So it's the same. It's the same idea as of disk method. Where instead of it being f of x squared, it's r squared minus little r squared. So this little r represents our whole, and this represents the space, like the actual shape, the actual volume of the shape. So if we didn't have a whole, we have the same formula, just with a different letter. So, r squared, I'm just going to write it again. So, we have our graph here, f of x, which equals 4. So we know that f of x equals 4. So we're just going to write right away, big R equals 4. And we have our bounds, y equals 1, x equals 0, and x equals 4. And our little r is this distance there. That's our whole. So we're going to write that one right away too. R equals 1. All right, so now we have all the things that we need, so we can just write our formula down. It's from 0 to 4, I believe. So 0 to 4 of big R squared, 4 squared, minus little r squared, 1 squared, dx. All right, so we have integral 0 to 4, 16 minus 1 dx. Pi times the integral of 15 dx. All right, and now we're back to simple calculus. We've got pi times 15x from 0 to 4. Plug in our bounds and we just get 60 pi. And I believe that is what we got by using geometry. So, way of checking your work, I guess. All right, so let's do one more of those. I mean, we'll be doing a couple more of those, but in different ways. We're going to do f of x equals, let's see, x plus 4 bounded by y-axis y equals 2 and x equals, let's do it to 4. All right, so we have x plus 4. We'll say that this is 4. And a very bad line. And that's our f of x. So then here's y equals 2. And x equals 4. Let's say is about there. Y-axis, which is just there. And now we have our region, which is this. And we're revolving it about the x-axis. So here I'd encourage you to pause it and make sure that you know how to do this stuff. But I'll do it right now. All right, so big R. That is this distance all the way down to the axis of rotation, which is the x-axis. So that distance is just our function. So big R equals x plus 4. And our little r is the whole, which is from the x-axis to 2. So little r equals 2. All right, so we have pi times the integral from, what was it, 0 to 4? 0 to 4, x plus 4 squared minus little r squared, which is 2 dx. All right, so I'm going to square all this out and make our lives a bit easier when we're integrating. So square the first, double the product, square the last, minus 4 dx. Combine like terms, we get 2, I integrated early, 2x plus 8x plus 12 dx. And now we're just back to integrating. So we have 2, or no, I was taking the derivative, x cubed over 3 plus, let's see, 4x squared plus 12x from 0 to 4. Let's write that 0 a bit better. And now we plug in our bounds. 4 cubed is 64 over 3 plus 4 cubed again, 64 plus 48. All right, so add these together. This is kind of annoying with the thirds. Let's see, we get 100, 112, 64 thirds. What is that? 336 plus 64. Straight up 400 thirds, I think, if I did my math right. If not, I'll put on the screen probably. that I did the math incorrectly, but I think that is correct. 400 pi thirds. And here you could technically do geometry, I think, again. You'd have to calculate the volume of like two different cones, which would be a pain. So I wouldn't suggest that in this situation. But do whatever you think is fastest for you. All right. So it's gonna get. I mean, it's not too complicated so far, right? But here, I'm gonna give you a bit of a challenge. So we have x squared, f of x equals x squared. So we'll draw that out right now. And we're going to have it bounded by the, let's see, the y-axis and the line y equals 4. So y-axis and y equals 4. So that shape is this right here. So I'm actually going to ask you two questions here. So A will be volume generated when revolved about the x-axis, as we have been doing. And the next question will be, the volume generated by revolving about the y-axis. So we're changing it up a bit. So this one you can do on your own. I'm not going to go over it again. But basically all you would do is from about the x-axis. Actually, this might be a good one to go over. Yeah, we'll actually do both. So for A, we're told our bounds is y equals 4 and the y-axis. Since we're rotating it about the x-axis. So you need to be careful here because we're not integrating from 0 to 4, right? Because where this intersects, that point right there, is not x equals 4. It's x equals 2. Because where it intersects y equals 4, f of 2 equals 2 squared, which equals 4. So that's where it intersects. So we're integrating from 0 to 2. Got to be careful when it asks you questions like that. So 0 to 2 of x. Actually, this is a really good one to go over. So again, we have a hole, this distance, and this distance. So our big R is from here to here, right? So that's actually just y equals 4. So we can do 4 squared minus little r squared. It's x squared is that distance right there. So this distance is given by f of x. All right, so we can do our math. So pi times the integral of 16 minus x to the fourth dx. And now we take the integral, so 16x minus x to the fifth over, oh, that's a really bad 5, over 5 from 0 to 2. Plug in our bounds, we get 32 minus 2 to the fifth is 32, I believe. So then we're left with 128 over 5 pi, I believe. So that's how you get A. And that's stuff that we've been doing. A little more complicated because you have to think about what your R's will be. But we'll move on to B, which is asking an entirely new question. So revolved about the y-axis. So we'll draw it again. So it was bounded by y equals 4. So there will be multiple ways to do this problem later on. You'll be given the shell method. But here, since we only know washer method and disk method, we're going to try that. So disk method and washer method is taking the volume, taking the area of a bunch of shapes stacked together, right? Remember how you have, if you have a circular piece of paper and you stack a bunch of them on top of each other, you generate a three-dimensional shape. So the radius of that circular shape is perpendicular to the axis of rotation. So before, we've been doing it, rotating it about the x-axis. So let's say we had our function right there. The radius is perpendicular to the axis of rotation, if you remember what perpendicular means. So if we're taking it, if the axis of rotation is the y-axis, we need our radius to be perpendicular, which means we're actually going to do it in terms of y. And that means our function also needs to be in terms of y. So let's cut all this out. So we have f of x equals x squared, or y equals x squared. Well, to get it as a function of x, we just have root y. Well, technically plus or minus, but that's irrelevant for this problem, equals x. So now we can do our formula the same as we've been doing. Let me use a different color here. We have pi times the integral, and since we're taking it perpendicular to the y-axis, our bounds of integration, our a and b, will be from the axis of rotation to the bound, which is this distance. which is parallel to the axis of rotation. So we're actually doing it from 0 to 4 because remember this function is bounded by, I should say, y equals 4. All right, so now we have our function in terms of y. So we're y, and we're still squaring it, dy. So we have pi times, go through this step by step, y dy, and the integral of y dy is just y squared halves. This should not be an integral symbol. From 0 to 4, and we plug in our bounds, we get 16 divided by 2, which gives us 8 pi. And notice that's not the same answer that you get when rotating it about the x-axis. We got 128 pi fifths. And that's because it's in an entirely different shape. We're revolving it across a different axis. So you're not necessarily going to get the same volume. There are situations where that would happen, but it would have to be like a linear function. So it's pretty rare that that would happen. But now you know how to revolve it about both axes. And sometimes it will ask you, let's just do a quick one here. Sometimes you're given, we'll do f of x equals x. We'll just stay simple. And it says it's bounded by the x-axis, y-axis, and the line x equals 3, for example. And it will tell you it's revolved about y equals -1. Now, this is not a cause for worry. It's the same idea. You just have to think a little bit harder about it. So that's x equals -1, or that's y equals -1. This is x equals 3, our bound. So this is the shape. And we're revolving it about y equals -1. So we'll have a hole here, and the distance, our big R, is that distance. So our little r, since it's this distance, it's from the x-axis to y equals -1. So 0, I'll just write this out. 0 minus -1 equals 1. So that's our distance. That's our little r. So we have pi times the integral of our function, our big R, which is x squared, minus little r squared, which is just 1 squared. And our bounds is from 0 to 3. So 0 to 3. And you can do the same math you've been doing. This is a really weird pi symbol. Integral of x squared minus 1 dx. So we have 2x. Oh, no, I took the derivative. X cubed over 3 minus x from 0 to 3. And we have pi times 27 over 3 minus 3, which this equals 9. 9 minus 3 is 6. So we get 6 pi. So that's what you have to do. That's all you have to do if it's a different axis than the x-axis or the y-axis. You could also be asked revolved about x equals -2. You'll never be asked to revolve it about an axis that intersects with the with our shape. So like if you were asked revolve, like you would never be asked revolved about let's see, x equals +2, because that would give us this axis of rotation here, and that would create a really weird shape. So don't worry about situations like that. If that's a situation that pops up, there's typo. So make sure to bring that up, because then you'd have like intersecting volumes. That would be, at least I don't know how to calculate that. I don't know if you can, but. So moving on, we've gone over disk and washer method. Disk method was pi times the integral from a to b of f of x, that looks like a p, f of x squared dx. And washer method was pretty similar, but all that's different is that it takes into account a hole in the function represented by r squared. So now we've got shell method, where instead of integrating perpendicular to the axis of rotation like we do in disk and washer method, in shell method we're integrating parallel to the axis of rotation. So the shell method is simply just 2 pi a to b of r x h of x dx. And you can also do it in the other way, just like how you can do washer method in both ways. You can do r of y h of y dy. So what this means here, we'll draw it out. Let's draw a little parabola for an example. So if we are integrating where we're rotating about the y-axis, then we draw our, what a lot of people do is draw a rectangle to properly visualize it. And this will be r, and this will be our h. So the volume would be equal to the integration from a to b of r of x, h of x, dx. So the difference there, so like if we were trying to use shell method, if we were trying to use disk method, instead we would do a to b. Well, in this case, you would need to use washer method because there's a hole right there. It would be big R squared minus little r squared dy, because you would be doing it perpendicular to the axis of rotation. So when you're using shell method, the h will always be parallel to the axis of rotation. See how this line is parallel with the y-axis, which is the axis of rotation. So to continue the example, if we have the same graph and we want to rotate it about the x-axis, our rectangle would be drawn like this. And our h would be this, and this would be our r. So in this case, the function would be 2 pi times the integral, oh, sorry, I forgot the 2 pi here. Pi there, 2 pi on the shell method. So the formula would be 2 pi times the integral from a to b of r of y h of y dy. If you were using washer or disk method in this situation, you would actually not need to account for a hole because there's no hole in that distance. So it would simply just be f of x squared dx. Some situations, shell method would be easier. I generally lean on disk method or washer method. It's generally easier for me to understand, but we'll go through some problems nonetheless. So I'm going to do 2 problems with you where I do both shell method and disk method or washer method. And then I'm going to have one more challenge problem that I'll go through. And of course, I'll have a worksheet posted in the description that you can look at if you want some extra problems. So we'll do root x. Well, no, we've already done root x. We'll do x cubed about the y-axis, rotated about the y-axis, and it's going to be bounded by the x-axis and the line x equals, we'll do 3. So we'll draw it out real quick. We're rotating about the y-axis, which means our rectangle will be parallel to the y-axis. So this is our h, and this is our r. So in this case, our r will simply just be our x because we're measuring how far along we are in the function. So let's write out our function. We have 2 pi times the integral from 0 to 3, because that's what we're bounded by, of x, which is our r of x, times h of x, which will be this distance here, which is our function, x cubed, dx. So 2 pi times the integral from 0 to 3 of x to the 4th dx. And now we can integrate 2 pi times x to the 5th over 5, 0 to 3. I believe 3 to the 5th is 243. So 2 pi times 243 over 5. And that equals, let's see, 486 fifths pi. So that's our answer. We got that pretty quick from that method. I believe this might be one of those situations where it's actually easier to use shell method, but we can test it. So we have our function. And we're going to try to do disk method this time. In this case, we'll need to use washer because there's going to be a hole this distance right there. So our little r will be the function in terms of y. So x cubed equals y. So x equals the cubed root of y. That gives us this distance here. So we have pi times the integral from 0 to, ooh, this is really ugly. So we need to plug in 3. I guess it's not that bad. So it's, well, it is. It's from 0 to 27 because where this intersects the line is y equals 27. And we're integrating perpendicular to, we're integrating in terms of y. So 0 to 27 of big R squared, which is simply the distance from the axis of rotation to our bounded, our bound, which is x equals 2, right? Or x equals 3. So it's going to be 3 squared minus cubed root of y squared dy. So yeah, this is one of those cases where it's actually going to be easier to use shell method. So pi times the integral from 0 to 27 of 9 minus y to the 2/3 dy. Now we can integrate 9x minus, let's see, 2/5 y to, or is it 3/5? 3/5 y to the 5/3 from 0 to 27. Okay, so pi times 9 times 27, what is that, 180, 63, 243, minus 3/5 times 27, the cube root of 27 is 3. 3 to the 5th is 243. And how I like to visualize this is I have 5 parts of 243 and 3 parts of 243. So then I am left with 2 parts of 243. So 2 times 243 equals 486. And don't forget the denominator. So we're left with 486 fifths pi. If that math didn't make sense, don't worry. Just check it in your calculator. That's how I like to look at it in my mind. But we get the same answer as we did using the other method. So I'll do one more of those. I got to think of one. We'll do it rotated about, let's see, I did that one about the y-axis, right? About the y-axis, so we'll do this one about the x-axis. F of x equals root x, and bounded by y-axis and bounded by y equals 4. So function looks like this, and we're looking at this shape right here. I believe this will also be easier using shell method. So we draw a rectangle perpendicular to the x-axis. So this is our h, and this is our r. So let's see, our h is going to be, well, first we need to write x in terms, the function in terms of y. So we'll have x equals y squared. So we're integrating 2 pi times the integral from 0 to 4, because we're given y equals 4. 0 to 4 of, let's see, y squared times r of y, which is simply just y, because it's just measuring how far along we are up. So we're left with 2 pi times the integral from 0 to 4 of y cubed dy. Forgot to write the dy there. And now we can integrate 2 pi times the integral, so y to the 4th over 4 from 0 to 4. Let's see, 4 to the 4th is 256 divided by 4 is 64. So 2 pi times 64 equals 128 pi. Perfect. And we can do it the other way. I'll do that real quickly. Well, it actually won't be very quick because it's kind of ugly. So we're doing it from, what was it? Y equals 4. So we're doing this shape here. So, oh boy, yeah, this is really ugly. So from 0 to 16, because y equals 4 at x equals 16, don't forget the pi, of, so we have to use washer method. So our big R is simply just 4 squared minus our little r, which is this distance, which is, well, let's write it in green, root x squared. Actually, this might not be too bad. So now we're left with pi times the integral of 16 minus x dx. Yeah, that's not too bad. Pi, now we're integrating 16x minus x squared halves from 0 to 16. 16 times 16 is 256 minus 16 squared, which is also 256 halves. So then 256 minus 256 halves is just 256 halves, which equals 128. And don't forget the pi. 128 times pi is our answer. And that is the same as what we got here. Sweet. All right, so I'm going to do one more problem. And then I might have some things posted in my description so that you can look at those problems and do them on your own. But let's see. We'll have f of x equals, okay, wait. I'm going to write this fully out. So give me a second. All right, so here's the problem here. We're actually going to be given two functions, f of x and g of x. So I'm going to draw this out real quickly. So we're going to represent g g of x in red and f of x in blue. So g of x is x squared, our lovely parabola. That is not a parabola, that is a line. And we have root x plus 2 for our other function, which looks a little something like that. So the area is this ugly shape. But you've learned everything that you need to know, because all you need to know is the distance, our r squared, big R squared. Ooh, let's not use orange. We need to know our big R squared and our little r squared. So if we erase this, we're rotating about the x-axis. This distance right here is going to be our big R. And this distance right here is going to be our little r. Well, we actually know what those are. This distance here is just f of x. So we can write that down. We have pi times the integral, we're not going to write our bounds yet, of f of x root x plus 2 squared. That's our r of x. That's our big R. And we need to find our little r, which is this distance, which is actually just our g of x, x squared. So minus little r squared. And to find our bounds, we have to find where these two functions equal each other, which I don't know if it's a very nice number. Let's see. 2, 4. Yeah, it's not a nice number, so I'll need my calculator for that. So they intersect at x equals, oh boy, 1.83. I'm just going to round it to. And we're going from 0 to 1.83. So this is really just more annoying than it is hard. So we're going to square it out, 0 to 1.83. Root x plus 2 squared. Let's see, square the first, double the product, square the last, minus x to the fourth, dx. So pi times the integral from 0 to 1.83 of, oh, I guess we can't combine any like terms. Man, this is a really ugly one, but we'll still do it. X squared halves plus 4x to the 1/2, which we'll rewrite as 8/3 x to the 3/2 plus 4x minus x to the 5th over 5 from 0 to 1.83. All right, so I'm just going to plug this into my calculator. All right, so don't trust this answer completely, but what my calculator spat out to me was approximately 35.498. So somewhere around 36. I might have typed it in my calculator wrong, but yeah. Not really a hard problem, it just introduces you to a new gimmick. I'm sure there are nicer problems out there than that. But just all you really need to know is that there can be two functions in a system, just don't freak out. Realize that it's kind of the same thing that you've been doing, just with a second function. All right, that's it pretty much. So I hope you guys understand it a little better now. And yeah, thank you for watching, and I'll see you in the next one.